Whoa, back on the DraftScience channel, doing another one of these PBS Digital Studios, the real meaning of E equals mc². So I spared you the commercial. So yeah, I'll just explain how, not quite fella, or, you know, why it's different than they think it is. Yeah, that kind of thing.
Hydrogen atom has less mass than the combined masses of the proton and the electron that make it up. That's right, less.
Right. So again, the free particles would obviously have a different disposition than bound particles. And the whole idea of this happening anyway is sort of perhaps an illusion, this whole standard model of spinning things and all that kind of stuff. It's all magnetically connected, and there's no momentum in these objects or any of that kind of stuff, and blah blah blah. They're all made out of quanta. They're not things in themselves. So yeah, when you liberate them, they have to change their form. Would be it's like in chemistry with the shared electron. If you free the things, then you're going to end up with an ion somewhere. You're going to end up with something missing a bit. And so if you measure them with the bit, then they're going to weigh more than they would in the chemistry, because the chemistry is sharing bits. Kind of looked at that way. But the point is, all these things, the energy is just quanta. It is a thing, and it does possess it. And so how much things you possess is how much your real atomic weight is. How many things are occupied in that space? How many BBs? That's what it comes down to. How many fish are in the school? And that's all there are, nothing else.
Something way less than the sum of its parts, because of this. And today, we're going to clarify what the most famous equation in physics really says.
Just called it the most famous equation. And then
E equals mc² is probably the most famous equation in all of physics. But in his original 1905 paper, Einstein actually wrote it down differently.
Right. So again, now he's quote mining Einstein. So now he's telling Einstein, this is what you really meant, right? Is what you wrote originally. You didn't mean to revise it and say, well, wait, it makes more sense if you just multiply times c², because basically c² is a representation of the quanta again. So it doesn't really matter. Divide or multiply, you're still going to have relationally the same number. You're not changing any of the components realistically. It's not plus and minus. You know, division and multiplication are not the same as plus and minus in the inverse. They don't have the inverse effect. They just change an equation from a point, a decimal point. That's all they do. They just change the decimal point. So why you bother playing a game like this anyway? Right? I mean, people who know math know that dividing doesn't do anything different than multiplying in terms of it just changes the scope of the perspective. It doesn't change the relationship.
M equals E divided by c². That's because, at its core, this cornerstone of physics is really a lesson in how to think about what mass is.
Right. So says you. So again, I'm saying that you're not thinking about what mass is in any kind of rational way. You see photons go into atoms and you presume that the photon changes into something else, that it's not what it is still. Or electrons or anything going in. Energy goes in. And you're thinking the energy isn't what is already in the matter. The matter is already full of that stuff. And even when they explode nuclear bombs and you see all the radiation fly out of that thing, you're still not getting it. The little tiny bits flying out, the energy being released, and you're still not getting it. That the only thing matter's doing is containing energy. It's not changing it, it's not doing any of that stuff, it's just trapping quanta bits of energy.
You'll often see statements like, mass is a form of energy, or mass is frozen energy, or mass...
Well, there you go. Frozen energy might be a good way to say it, just in the sense that it's trapped.
...can be converted to energy. That's the word.
Well, yes, and converted is a not entirely stupid way to say it, in the sense that you're converting it from trapped to untrapped. You're converting a prisoner into a free man. But the man is the same in both places. Whether he's free or in a cage, it's the same thing. It's the same man. Same bit.
First one. Unfortunately, none of these statements is quite correct, so trying to make sense of them can be frustrating.
Well, I don't think you're quite correct, so there, ha ha ha.
I think instead we can get a better sense of what m equals e over c squared means if we start with some things that it implies that seem at odds with our everyday experience of math. Here's a pretty mind-blowing one.
Oh yes, blowing the mind once again.
Even if two objects are made up of identical constituents, those objects will not in general have equal masses.
Right, so they won't be in exactly the same state if they're in a different state. Wow, what a surprise. I mean, if I'm doing something, I am not the same as if I'm just sitting. Yes, it's true. But it really depends on whether I'm consuming, okay, potential energy or not consuming it, in the sense releasing it. So in that sense, if I'm just releasing something, well then, well, it doesn't really matter.
The mass of something that's made out of smaller parts is not just the sum of the masses of those parts.
Yes, it is. You know, it is. The parts in the condition they're in the thing. Again, you can't measure these parts anyway, okay? This idea that you can build scales to measure the weight of an electron is just kind of silly anyway. But the point is that the thing is different. So there's no point in saying, look, it's different. Well, of course it's different. That's why it weighs different. It's because it's in a different environment. It's in a different condition. You know. Yeah.
Ed, the total mass of the composite object also depends on, 1, how its parts are arranged, and 2, how those...
Well, I would argue that the arrangement doesn't matter if it's still the same component. So arrangement doesn't matter unless you're saying arrangement isn't like this, but the arrangement is there's now shared electrons between something. So again, if the arrangement is forcing, obligating the chemistry to have another electron, well then obviously it's going to weigh quite a bit more.
Parts move within the bigger object. Here's a concrete example. Imagine...
The movement, I don't think, really substantially matters, but here's an example by my theory. So by my theory, all these little bits are all in everything. Everything's just moving little bits, little BBs. And the thing that you can do is you could change, let's just say A, B, and C represented directions. C was this way, A was that way, B was that way, and there was a D here going the other way. So it was all equal. And then I could add another A. I mean, I can add another quanta to this arrangement, so then it would have two A's, and so then it would be tending to move in that direction, because A is that way, right? So I could add an A, or I can convert a C into an A, and now it'll have that disposition and also have this disposition because it's lost balance in that other direction. So I can either convert what exists into some other direction, or I can add a component. So obviously when you add a component, you're going to add mass. When you change something that already exists, like you give me velocity, the idea that I would have to gain mass as I gain velocity, I could if I'm adding letters to my quanta, to my structure, because I can hold them, because there's some element in me that can behave like a battery and I can collect a certain directionality. Then I can gain weight. But also, just as realistic, I can just have the matter that I already contain have its letters changed, and therefore I'll move in a direction. So there's no obligation to gain mass as you gain acceleration in any significant matter.
Wind-up watches that are identical atom for atom, except that one of them is fully wound up and...
Well, I mean, there's no point in saying identical atom for atom and then talk about how they're different. One's running, one's wound, so that's not a fair comparison. Is this watch wound and ready, and you're just the only difference is that you haven't hit the go button? Well, then these two things are going to weigh the same. This one's going to start weighing less because it's going to start releasing its potential energy.
Running, but the other one has stopped. According to Einstein...
Well, run out. Maybe you should say those words. That watch is run out, so it's lost its energy. That's right, it's lost capacity to create movement, which often creates waste. So, obviously, if this clock was perfectly efficient, and it wasted nothing, there was no heat generator, no other way of losing any quanta, any force flying off of it in its movement, then it would stay the same weight. But It's going to lose because it's going to waste.
The watch that's running has a greater mass. Why? Well, the hands and gears in the running watch are moving, so they have some kinetic energy.
Yeah, but they only have kinetic energy because they're converting potential energy.
There are also wound-up springs in the running watch that have potential energy. And
Right, again, so you're saying this watch doesn't have anything wound. So you're just comparing a run-down watch to an unrun-down watch, which is like comparing a full battery to an empty battery, and no surprise there.
And there's a little bit of friction between the moving parts of that watch that heats them up ever so slightly so that its atoms start jiggling a little bit. That's thermal energy, or equivalently, randomized kinetic energy.
Right, but it's still, that thermal energy is being created out of losing its potential energy. So that's called waste. So it's losing weight. This watch is losing weight fast. This one is already expired, and that's all you're really demonstrating here is full battery running down, empty battery staying unwound. And so you're just watching this get less heavy and saying it's heavier. Well, it's only heavier not because it's moving, but because it has potential energy in it, because it has more quanta or more capacity to produce these extra quanta, to produce this, to liberate quanta.
A more microscopic level. Okay, got it? Now, what N equals E over C squared says is that all that kinetic energy and potential energy and thermal energy that resides in the watch's parts manifests itself as part of the watch's mass.
Yes, all of this stuff equals quanta. All of these elements are the same thing. It's all just energy. It's all just quanta. And if you lose quanta, you'll lose weight. If you retain or if you put prisoners in jail, your jail gets heavier. If you let prisoners loose, your jail gets lighter. Not complicated, really, at its root. Not complicated.
You just add up all that energy, divide it by the speed of light squared, and that's how...
No, you don't bother doing that dividing thing. Like I said, you multiply because it makes more sense.
How much extra mass the kinetic and potential and thermal energies of the parts contribute to the whole. Now, since the speed of light is so huge...
Well, kinetic, potential, and thermal. Again, potential is the mass of the object. The object is full of potential energy, as nuclear bombs demonstrate. So potential energy isn't like just winding the spring. It's in every element of the atom, in every quanta bit that it's made out of, in every bit of directional information that's trapped in it. So, I mean, it's made out of potential energy because it is energy. I mean, potential is just a way of describing a kind of energy, and a kind of energy is like just a kind of quanta, a state that a piece of quanta is in. It's either in the prison or it's not in the prison.
Huge. This extra mass is tiny. Only about a billionth of a percent of the total mass of the watch. That's why, according to Einstein, most of us have always incorrectly believed that mass is an indicator of the amount of matter in an object.
Well, it's not. Obviously, the matter is the amount of matter. That's not what people think. And that's not what Einstein's equation says. It's saying that matter is energy. It's just trapped in the matter. It's condensed. It's consolidated energy. It's exactly the same stuff that's out there. It's just in a form that's different than the out there stuff. And the only time we see the energy is when we create, as I've pointed out, an imbalance in the field of energy at any one location. You'll notice there's energy if at a certain location there's a preponderance to go in a certain direction because of an imbalance in what the total field is doing in that location. But the energy is always there. Energy, the whole universe is energy. And like again, you only see the imbalance. You only see when the wind blows. But it's all made out of wind that isn't doing any winding that you can notice. It's not a good way to say it. It's when it's balanced, it's invisible. It can't be detected. We detect it when it's imbalanced. That's it. That's what makes energy visible. But energy is essentially the nothing, the ether, is made. Space is full of energy. You just can't detect it because it's balanced energy.
Everyday life, we just don't notice the discrepancy because it's so small. But it's not zero, and if you have perfectly sensitive scales, you can measure it.
Well, again, you don't need perfectly sensitive scales. We already know this concept, and you're even going to bring up this concept that, with a flashlight or a battery, that when you put energy into something, when you give it potential, which, stuff you can realize, that there's an actual impact to that, that those are actual quanta going somewhere. Those are actual prisoners filling up the jail.
So wait a second. Am I saying that individually the mass of the minute hand is bigger because the minute hand is moving? No, that's an outdated viewpoint. Most contemporary...
Well, whatever. The point is, though, is that it can have greater mass if it's collected more quanta as the reason why it's moving. Is because all of its electrons are now charged because they've been given this directional, they have more B's. And they just grabbed a bunch of B's out of the environment. Instead of changing its own structure, it actually just gained more of some direction, and therefore is moving in that direction because it absorbed more energy. The capacity to absorb energy has to be considered.
Physicists mean mass while at rest, or rest mass, when they talk about mass. In modern parlance, the phrase rest mass is redundant. There are lots of...
Yes, I'll agree with you that it's pretty redundant to talk about rest. It's not even redundant, it's almost oxymoronic to talk about rest mass when you can't really make an atom rest.
Reasons for talking this way. Among them, that rest mass is a property all observers agree about, much like the space-time interval that we discussed in a previous episode. This all gets a little bit more complicated in general relativity, but we'll deal with
that's just crock of shit stuff, so it's not going to go there, buddy.
that another time. For us, today, the m in m equals e over c squared is rest mass.
Again, I don't know why you're doing that, right? I mean, Einstein lived a pretty long time. I think if he wanted people to say m equals e over c squared, I think he would have said, fix that. I don't like it. It's not what I meant. So you're basically just rewriting Einstein and saying after Einstein's dead, oh, I'll fix that for you. You had a whole lifetime to tell them they had it wrong, and you didn't bother doing that. I mean, you talked about all kinds of things, spooky action, you didn't just tell people, hey, wait a minute, don't do that multiplying thing, do this division thing instead. I mean, that's kind of bogus, buddy.
You can think of it as an indicator of how hard it is to accelerate an object, or an indicator of how much gravitational force an object will feel. But either way, a ticking watch simply has more of it than an otherwise identical stopwatch.
Well, again, you're saying otherwise identical. I just don't... What does that mean? That doesn't mean anything. You mean wound or unwound. If it's a wound watch, then you've put a bunch of quanta into the watch. You've put force into it to force the unnatural condition, so to speak. You've aggressively changed the chemical circumstances of the molecules by applying force that they've retained, and that they will release that force, elastic, with a kind of elasticity, because you've added it. You've created by bending it, you've created opportunity to stick more stuff to it. So now it's heavier because it's more quanta in it. And as you allow it go to a natural condition, it will release that extra.
Some more examples might help to clarify what's going on here. Whenever you turn on a flashlight, its mass starts to drop immediately.
Right, so then why didn't you just talk about it in terms of flashlights, right? Why did you bother with this watch thing where you basically broke the analogy by not saying explicitly, I mean a watch that isn't wound?
Think about it. The light carries...
Yeah, so compare a flashlight with a charged battery to a flashlight with an uncharged battery and say, look, the flashlight with the charged battery weighs more. Duh.
Energy, and that energy was previously stored as electrochemical energy inside the battery and thus manifesting...
Well, again, electrochemical energy, let's understand what that means. What that means is that a bunch of empty locations in atoms became full of extra quanta bits to chemically bond the object together. So the bonds became richer, thicker with quanta. And that's why some chemistry will allow you to do that. The chemistry will allow you to put a bunch of extra electrons in there. And those extra electrons represent an amount of quanta, 1,000,000 quanta.
As part of the flashlight's total mass. Once that energy escapes, you're not weighing it anymore. And yes, since the sun is basically an enormous flashlight, its mass drops just by virtue of the fact that it shines.
Just by virtue of this fact that it shines. And see, he's going to say something here that's just so wrong.
About 4 billion kilograms every second. Don't worry, Earth's orbit's going to be fine. That's just 1/1000,000th of a trillionth of the sun's mass and only 0.07% of the sun's mass over its entire 10 billion year lifespan.
Right, but it's still a lot of wildebeests.
So does this mean that the sun converts mass to energy? No, this isn't...
Okay, no. Yeah, it does, quite obviously. Okay, fusion and fission, that's exactly what's taking place. You're basically changing atoms. You're doing alchemy. You're changing one element into another element, and in the process of doing that, you have leftover bits.
Alchemy. All the energy in sunlight...
See, he just said it. It's not alchemy. It is. I mean, it's the whole thing is a big alchemy engine, fuckhead.
Converts mass to energy. No, this isn't alchemy.
There, it isn't alchemy. Did you hear that? I mean, a physicist who's saying the sun isn't performing alchemy. I mean, it's smashing hydrogen atoms together, making helium, and having the leftover nuclear bits, right? The extra protons and neutrons, whatever, that are left over because there's a difference in the nucleus. You know, there's not a complete... You're basically only using... You know, your 2 hydrogen atoms, you're only using 80% of them to make your 1 helium, and so you have a bunch of extra bits that fly off, and that's the sun's energy. That's alchemy. You're changing hydrogen into helium. That's frickin' alchemy.
All the energy in sunlight came at the expense of other energy, kinetic and potential energy.
Kinetic and potential energy. No, it came because atoms were full of quanta, were converted into another. The jail was remodeled, right? So the jail had 10,000 prisoners in it. You decided, we're going to combine these two 10,000 prisoner jails, and we're going to make one jail that holds 15,000, right? And so, yeah, there's no room for the extra 5 anymore. So, yeah, see, those guys go free. It's not that proportion, but I'm just saying, it's more like... you know, it totals up to like 19,000 out of the 20,000 or something. You know, it's only 10% or whatever, so it's released. But the point is that's a lot of energy when you consider atoms and E equals mc². It's a lot of quanta c². C² quanta is a lot of little BBs.
Of the particles that make up the sun. Before that light was emitted, there was simply more kinetic and potential energy contained within the volume of the sun.
Well, again, to call it kinetic and potential energy is kind of confusing, because the potential is in the every inch of the atom is potential energy. Every inch of the atom is a quanta of energy. Every bit of it is made of a quanta of energy, a quantizable piece of energy, in the form of these photons and other kinds of radiation. So, I mean, it's just a perspective. It's just understanding that these photons are just one frequency, okay, and that we see them. And we understand the difference between, well, microwaves are doing exactly the same thing as these visible photons, and we understand that radio waves are doing exactly the same thing as these visible photons, and cosmic rays are doing exactly the same thing as these visible photons. It's just that they're not visible because they don't impact electrons in the same way, and therefore our brain can't make a sense organ for them because there's no way to sense them, at least with biology. And that's the only distinction. And the fact is that gravity is the same thing. Gravity's made up of these little bits of quanta. And the difference between gravity and light, you know, that you see, is merely the fact that you can see the light and you don't see the gravity. But the gravity is doing exactly the same thing. It's bathing you in straight-lined vectors from all directions in the universe.
Manifesting as part of the sun's mass. Those 4 billion kilograms that the sun loses every second is really a reduction in the kinetic and...
4 billion kilograms? That sounds anorexic.
Potential energies of its constituent particles. What we've been weighing is the...
Yes, that's exactly it. Constituent particles. But you don't even understand what particles are, because guess what? Neutrons, protons, electrons, these are not particles. Quarks aren't even particles. They're a mass of BBs. They're a school of fish, okay, that has a particular kind of little swirl. But that's it. It's still just BBs.
energies of the particles in objects all along. We just never noticed it. Another example. Suppose that I stand with a flashlight inside a closed box that has mirrored walls and is resting on a scale.
There we
Will
go.
the reading on the scale change
Watch
if
this.
I turn on the flashlight?
Watch this.
Interestingly, no. The flashlight alone will lose mass, but the mass of the whole box and its contents will stay fixed. Yes, it's true that the scale is registering less electrochemical energy, but it's also registering an exactly equal amount of extra light energy that we're not allowing to escape this time. That's right. Even though light itself is massless.
There you go. Even light itself is massless. So he just took away the quanta in the energy. Okay, he just said the light's massless, and yet when you release it, somehow it has mass because it's compensating for the lack of mass that the flashlight has. So if I shoot this light in this closed box, and the light stays in the closed box forever, and then I take the spent flashlight out and put it in some other box, what I'm going to notice is the flashlight I took out and put in some other box is going to weigh less because this flashlight is charged and that flashlight will be spent. And I'll also notice that this box containing all this light that I spent the flashlight on is going to weigh the difference. The difference between the weight that the flashlight lost and the weight of this energy is going to be the same. Because the energy does have mass, and you're just fooling yourself to say photons aren't quanta. They are quanta. They are an element of the universe. And they should be given the appropriate whatever. They have a mass of 1. And then make everything else's mass relative to a photon, and you might have the right answer. You probably should say it has a mass of 2. Because the only way you can see a photon is you have to have at least 2 quanta. So you can have the period between them. You can't have a frequency if you don't have more than 1 coming at you. So yes, give light the mass of 2, and then make everything else relative to that.
If you confine it in a box, its energy still contributes to the total mass of that box via m equals E over c squared. That's why the reading on the scale doesn't change.
Well, again, does that, see, but what did he just say there? Did he really say anything? He basically just said, this doesn't have any mass, but it does have mass, quite obviously, because it's still in the box. And if I took the flashlight out of the box with a spent battery, it would weigh less. So obviously the stuff that came out of the flashlight has to weigh something because that's conservation rules.
Okay, here's the really fun part.
Oh. No, this isn't fun. A little bit fun, maybe.
The example we've done so far, things have weighed more than the sum of the parts that make it up. But at the top of the episode, I state...
Yeah, well, do you think he proved any of that? No, he didn't prove any of that. He didn't prove that these are same things. These are things in completely different conditions, and therefore, it's like saying the Earth weighs the same whether it has a moon or it doesn't have a moon. Obviously, the moon combines with the Earth to make a thing, a space, that has a combined weight.
That the mass of a hydrogen atom is less than the combined masses of the electron and the proton to make it up. How does that work? It's because potential energy can be negative. Suppose...
Okay, so this is the part where it goes way off the reservation. Okay, there's no such thing as negative energy. There's not. There's just, it's all charge is just an expression of extra. So you can have no extra, 0, which we call net, or you can have some relative position of charge. Charge is always relative. So anytime you establish a ground, your ground might be 10,000 volts, and you're just making 15,000 and calling it 5,000. So the scale doesn't have a negative. There's no true negative. That's another delusion here. There's no negative charge. There's weak charge and strong charge.
we call the potential energy of a proton and electron 0 when they're infinitely...
It's the grounding thing that's the trick. There's no real ground anywhere. So you are always creating arbitrary grounds relative to the charges around you.
far apart. Since they attract each other, their electric potential energy will drop when they get closer together, just like your gravitational potential energy drops when you get...
Okay, so he's saying my gravitational potential energy is dropping as I'm falling. That is another point where I just say that doesn't make any sense, because frankly, as I'm dropping, I'm accelerating at a quicker rate as I drop, and it isn't until I go beneath the Earth's surface that I start being liberated of that burden. So I mean, to say that my potential energy is dropping when my acceleration is increasing, I don't think that makes much sense.
Closer to the surface of Earth, which is also attracting you. So the potential energy of the electron and proton in a...
I mean, all he's really saying is he's calling it potential energy, the distance in the gravity, how long you'll stay in this gravity well, of acquiring acceleration, and saying this is the total energy, is the entire fall, and as you fall, you have less distance to fall. Well, quite obviously, but now you're creating a time element and calling this a way of quantizing energy. There's no time element in E equals mc². E equals mc² is basically, let's take a frozen section of the universe and say, what's the energy? And that's when it really works, is when you freeze it and say, at this exact second, this atom has how much quanta in it. And that's all there is. There's nothing else. So this is sort of an illusion, because this is measuring this gravity, again, is being converted. This matter, both these pieces of matter are being converted through acceleration. They're changing. They're gaining more arrows in a direction, but they're not changing their potential energy at all as individual elements. There really is no change in their energy. They're not losing anything or gaining anything in this process. They're merely acquiring acceleration. They don't weigh more.
Hydrogen atom is negative. Now the electron in hydrogen also has kinetic energy, which is always positive.
All right, weigh is the wrong word to use, because we weigh things on dopey scales, and dopey scales are going to weigh the influence of gravity. We're weighing the gravity of something. And so we're using gravity as an indicator of mass, but obviously what I'm arguing is gravity doesn't tell you at rest mass.
Due to its movement around the proton. But as it turns out, the potential energy is negative enough that the sum of the kinetic and potential energies still comes out negative. And therefore, m equals E/c² also comes out negative, and a hydrogen atom weighs less than the combined masses of it's parts.
Yeah, booyah. No, sorry. Yeah, no, that's not what's happening. Again, it's just about the BBs. BBs are the game. Everything is made of these BBs. Again, like I say, all these pixels, and all you have to do is understand that matter is taking those pixels and putting them closer together in an arrangement where they're no longer flying free, in the sense that their probabilistic orientation is always maintained. So if I go into the field, if I go into a completely balanced field with the letter A on my shirt, what's going to happen is it'll change to B, it'll change to C, it'll change to D, but it'll always come back to A more often, because when it changes, say, from A to B, the A is released into the field, and now the field has an extra A in it. And so probabilistically, that extra A is going to come home to roost, so to speak, and I'm going to have more A's on me than any other letter, because I introduced the A into that section of the field. And what we're really talking about is that the universe has different fields, different sections of the universe are in a different disposition. It's not even the universe, but even our local space has very different field constituents. You know, they're at a different temperature, they're at different... the quanta in those areas are moving in different ways, and there's different densities of them based on the matter that's in them. This atmosphere is thin compared to the dirt below me. So their fields are full of different quanta in different orientations, and so when I put the letter A in another field, it might have a different impact. But the point is as soon as I inject something into a circumstance, if I'm changed, my the change is conserved in the sense that whatever I was is going to be put into the field, and that field will, depending on how it's oriented, it could just, like a shooting a laser, it could just shoot it away and it's gone. It's not coming back for a long time. That representation of A-ness, or whatever you want to call it, is shot away, and it's probably not going to be anything in the local field to bring it back again. But in many circumstances it will be trapped in the local field, and so if I'm changed into an A, from an A to a B, the A is going to still be local, and it's going to come back. More probabilistic than any other letter. So I'll be A more than I'll be anything else.
In fact, barring weird circumstances, all atoms on the periodic table weigh less than the combined masses of the protons, neutrons, and electrons that make them up.
Again, that's only a circumstance based on whether you combine them. You know, I mean, just the idea that if you separate the pieces will not be the same as they are when they're not pieces. They have to have constituent binding bits, and you know, so I'm just saying, once they go out, once you release the prisoner, he has to buy clothes or something. You know what I'm saying? So there's some. The fact is that you can't measure these pieces. Number one, you can't measure their weight in any rational way. The only way you can measure their weight, just like a photon, is to have it impact some other piece of matter. So again, it has to be making a bond of some kind with that matter for you to be able to interact with it. So this argument is bullshit. There's no way to weigh these things, and you can't weigh a neutron independent of an atom. It's just silly.
Same is true for molecules. An oxygen molecule weighs less than 2 oxygen atoms because the combined kinetic and potential energies of those atoms...
Right, so I'm just saying that all he did was, they're saying that because they're presuming this negative charge thing, and so they're not even saying this is because we have evidence of it. They're just saying it because this is how we do the math. And sorry, that's just wrong.
And once they form a chemical bond, is negative. What about protons and...
Again, forming a chemical bond often represents disposing of excesses, because now you're sharing elements of yourself, and that's creating the bond. The bond is being created because you're ripping some skin off, so to speak, and then melding the two skin patches to each other. So I go up to another person. That's a little kinky, right? Yeah, maybe aliens do this, right? Yeah. And you just, you peel your face off, peel the other guy's face off, you smash the two heads together, they grow together, and now they're a Siamese twin. And what do you have left over? Oh yeah, you have a patch of skin. You know, that kind of thing.
Neutrons themselves. They're made of particles called quarks, whose combined mass is about 2,000 to 3,000 times smaller than a proton's or neutron's mass. So where does the proton's mass come from? Basically, quark potential energy.
Well, again, more potential energy. Well, it's all potential energy, so it's just silly to say, where's it come from? The matter made the matter, and it's in the matter. The matter's matter. The matter made the matter. No. It's all made of something else, quanta bits.
We did a nice episode on this that you can click over here to view. Every time he says gluons in that video, just substitute quark potential energy, and you'll have a roughly correct picture.
Right, quark potential energy is so much more sensible.
Sure, what's going on. Alright, what about the masses of electrons in quarks? At least in the standard model of particle physics, they're not made up of smaller parts. So where does
Right, so says you again. So the standard model again. Well, that's what they say. I mean, he's not even confident, you know. So yeah, why bother then? Why bother using the standard model when it's not going to represent the truth? Quarks are not particles. Quarks are made out of gravitons, quantons, whatever you want to call them. But that's what they're made out of. They're made out of BBs. They're made out of bits. Bits of energy. Planck bits.
Where does their mass come from? Is it some kind of baseline mass in the pre-Einstein sense of the word? Well, that's a subtle question, but crudely speaking, you can think even of this mass as being a reflection of various kinds of potential energies.
Well, again, potential energies is just, it's just a non-starter. It's quanta. This potential is just a silly word. The whole universe, the entire ether that's creating gravity is all potential energy, potential mass.
For instance, There's the potential energy associated with the interactions of electrons and quarks with the Higgs field. And there's also potential energy that electrons and quarks have from interacting with the electric fields that they themselves produce.
Right, again, so all this crap is just crap. There's no the fields are made out of quanta, everything's made out of quanta, so there's no, and there's certainly no negative energy. There's no such thing.
In the case of quarks, also with the gluon fields that they themselves produce. Okay? What about matter-antimatter annihilation? Doesn't that have to be thought of as mass being converted?
Well, understand, there's no such thing as antimatter. All they're really talking about is that there's two particles that might be a left and a right. And when they hit each other, they annihilate, which means they turn into energy. They release their quanta. So it's not really like, if you're going to call something antimatter, it really should be that it eats a piece of matter and nothing happens. No particle exists, no anything exists. It just eats it and nothing happens. It disappears. That would be antimatter. So I just think this is just such a bogus way of describing it. It's merely an anti-electron, if that's what you want it. But that, it still doesn't say it right. It's a destroy. It's left, right. It's up, down. However you want to describe it. It's two things that are not compatible. So use some kind of incompatible word to describe the fact that they will release energy. So they're door breakers. They're, let's see, I don't know how to. What's the opposite of prison? Anti-prison. Wrecking ball? I don't know.
Into energy? Interestingly, no. There's a way to conceptualize even this process as simpler conversions of one kind of energy to another. Kinetic, potential, light.
You didn't like conversion words before. You crossed them out. You put lines, red lines through the word conversion. Irritating.
So forth. You never need mass to energy alchemy.
You never need mass to energy alchemy. Well, again, that's exactly what most of the universe is doing. It's converting, certainly in the nuclear bits, mass into mass and releasing energy. It's doing alchemy, and even the chemical energy, in a sense. See how to describe it. Again, it's just using these little extra bits as glue, and so it's the peeling face argument. The bond is being made out of the fact that they're sharing something that they don't share when they're free. So they have to have a skin when they're free.
Please take my word for it. You don't actually have to talk about converting mass to energy ever.
Well, you really do. And see, and the other thing is you got to remember, when those atoms go together, it's like they're kind of jumping. A lot of them have to be energetically pushed into each other. So it's not even like the fusion is some sort of voluntary process. The fusion is like pushing the two heads right into each other and forcing them to exist in the same space. And that's why there's a release of energy, is because now they're sharing a hunk of space. That kind of thing. But the reason why they have energy is the very fact that, or potential energy, is the very fact that you did have to apply energy to force that arrangement.
Instead, the punchline of this episode has been that mass isn't really a thing at all. It's a property that all energy exhibits. And in that case,
okay, mass is a property. No. That all energy exhibits. No. See, that all energy exhibits. That's stupid. A property that all energy exhibits. Because you just said before that photons, which are energy, don't have mass. So you can't play this game with these words like this. This is just not correct. So mass, you either say photons have mass, either acknowledge that gravitons have mass, that these things are real things in the universe, and they affect the prisons, the wind blows.
Even though it's not correct to think of mass as an indicator of amount of stuff in the material sense.
Yes, it is an indicator of amount of stuff. That's exactly what it is. That's completely appropriate. That's exactly how you should think of it. Mass is an amount of stuff. That's exactly what it is.
You can't.
And energy, as you see it, is just energy revealed. That's all. The energy exists, and it's only when you see the imbalance in the field that you can see the existence of the energy. The energy is invisible as long as everything is frozen by no imbalance. But as soon as an imbalance happens, then you'll see the energy.
Think of it as an indicator of amount of energy. So,
but recognize again, the potential is in the mass. That was the whole point of what Einstein was saying. E equals mc². The frightening implication of it is that yes, you can make bombs that break atoms and you'll release a ton of energy when you do that. Because matter is just stored energy. It's all a battery. Some batteries are easy to tap. Some batteries are really hard to get the voltage out of. That's the only difference. Some batteries are really easy to get the voltage out of. Some batteries are really hard to get the voltage out of. That's all. Some have bigger locks on them, however you want to describe that, but it's all the same thing. All matter is energy, prisoner, wanting to be free.
Without realizing it, you've really been measuring the cumulative energy content of objects every time you've ever used a scale.
Right, okay, so now you just contradicted yourself because this is exactly right. Energy equals mass. Yes, it's stuff. These are the little bits of stuff, and that's what weighs the stuff.
I'm going to wrap up with 2 comments. First, Einstein's original paper on this topic is only 3 pages long and not that hard to read. We've linked to an English translation of it down in the description, and I strongly encourage you to check it out. Second,
yeah, I read it once. I probably should do that again, maybe do a video of it. Line by line or something. Maybe.
The challenge question to test your understanding. First, some background. Suppose you put 2 identical blocks side by side on a scale and weigh the combo, then stack them one on top of each other and weigh them again. The second configuration has more gravitational potential energy than the first because the second block is higher up.
I know, but this isn't weighing atomic weight, so again, this isn't really relevant, is it? You're weighing the imposition of more gravitons. That's the gravity is what you're weighing. The gravity is going into these objects, creating acceleration, and so when you put them on top of each other, you've doubled per square inch the gravitational. Well, that wouldn't matter because the scale was holding both of them before. So yes, you've upped the potential of the gravity because you've created a higher. All right, I have to. It's this distance. See this distance that's creating the weight, because now it's not only that gravity's getting blocked by one thing, it's getting blocked by the second thing, so that's where it gets the diameter matters, in that you're absorbing a percentage of gravity, and so this ends up being a higher percentage of the total gravity grabbed because of the fact that they're on top of each other. It's probably not the right answer either. Alright, I have to think on that one. But anyway, so then he's going to do a hammer example, so I'll wait until I think on those. But, I mean, obviously when you lift something, it gains potential energy. But the potential that it's gaining is merely the fact that you took it from a heavier place. So it's, yeah, okay, that's the way to say this. This is in the heavier place. And so, I mean, it's in the heavier place in the sense that, still not going to say that right. The closer you are to the Earth, the more gravity's pushing down on you. That's a truth. Now, if I take you and put you higher up, there's less gravity. So how could you have more mass? Alright, I still have to think on that one. Alright. I'll work on that. Maybe I'll add on this video. Maybe I'll think about it and then add on this video. That would be a good idea. Yeah, maybe I'll take a pause. That's what I'll do. I'll pause. Whoa, I'm back. Yeah. It's just a bullshit question, actually. So we'll go back to the box thing just for a second. Alright, so these 2 boxes are supposed to weigh more than if the 2 boxes are side by side. And it has nothing, this whole weighing thing is just weighing gravity. So again, that's not atomic weight. So it's really stupid, right? Because I could just say, well, if I put the scale in space, then the boxes don't weigh anything. Stupid. So it's just using gravity indirectly to measure mass, but it's not really mass you're measuring gravity's effect on mass, which is generally speaking consistent, but obviously, you know, at different levels of gravity, you'll get a different mass weight, and so it's not reliable. It's good for relative comparisons and exactly the same gravity, but it's absolutely useless if you're going to have different gravity, you know, different places in gravity where you're going to measure relative weight. So if I measure hydrogen on the surface of the Earth and I measure helium in space, that would be stupid because the helium will weigh less than the hydrogen. You get it? On a scale. So this is kind of just all bogus. So he should never mixed Einstein's equation, E equals mc², which is really about what's the nature of matter itself, what is atomic weight represent, which is the amount of energy the thing is capable of producing, the amount of BBs it's capable of releasing, and weight in gravitational fields. So when he calls this potential energy, like raising a box is somehow creating potential energy, it's not really potential energy of the box. It's not in the box. It's in the gravity. And the gravity, realistically, it's not potential energy in a sense, because it's just an illusion of your scales. Oh, that's really irritating because I'm busy. But anyway, I'll be back. Yeah, okay, let's see, where was I? Anyway, so who cares about this box stuff? You're not going to change the atomic weight of the boxes by moving them anywhere. It doesn't make any difference, so this was stupid. Alright, so going on, he plays this
But it will have more mass in the first. Keep that in mind for the following challenge question.
Yeah, like I said, it could be just an air pressure thing, you know. There's more surface area, blah, 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 blah. Some kind of bullshit like that. But he doesn't answer this question anyway, so it doesn't matter.
Suppose that every person on Earth simultaneously picks up a hammer from the ground. Would the total mass of the planet increase? And if so, by how much?
Okay, so again, this isn't, you can't count this as part of the mass of the planet. This is a gravitational effect, so you didn't change anything about the mass of the planet. It doesn't matter how dense, you know, if you spread the mass of the planet out, it's still the same amount of gravitational potential. So this is the part they just don't get, okay? The potential to be affected by gravity, to create gravity. And all you know, that's gravity is a manifestation of atomic weight, not volume, but weight. The number of the quanta, the amount of stuff that the gravity has to hit to go through. So again, he's measuring an external force. He's not measuring the thing itself. He's measuring the field energy applied to elements. And that's not a real measurement of atomic weight. So there is no, the atomic weight of this hammer doesn't change no matter where you place it, on the Earth, away from the Earth. It doesn't, no matter where you put it, the mass of the atoms in that hammer is exactly the same. So this is a bullshit question. So his answer is basically saying, oh yeah, well it took chemical energy to lift it up, and so there's no difference. And then he makes the qualification that if aliens came here and pulled all the hammers up, then the mass of the Earth increases slightly. No, it doesn't. Doesn't change. This is only a representation of energy released over time. Once again, the energy you release, you see, is energy that's made visible by the force of gravity. So it's gravity's energy that is essentially making this appear energetic when it falls. It isn't making it fall. The gravity's making it fall. It's not using any internal energy to do that. It's in fact being converted. All that's changing is the hammer has more arrows going down than the hammer has arrows going up, but it's the same number of arrows in the hammer. So this was sort of just bogus. But anyway, the whole thing was bogus because he shouldn't have combined weighing on Earth, which is is approximating. When you weigh something on a scale, you're just approximating atomic weight or mass, real mass, based on gravitational effect. And we know we could fool that by just putting a magnet underneath the scale, and then magnetic objects will appear way heavier. You know, so it's not a true measure. It's just an indirect way to assess, generally speaking, atomic weight. So we shouldn't have combined these two things. Einstein's equation has to do with the nature of matter itself, and this has to do with the nature of the field the matter's in, which are two different subjects. So I call bogus. I'm officially calling bogus. Yeah, there. I did my job. So anyway, till next time and such, so forth and whatnot.